Um, so we discussed fertilizers last week. I tried to emphasize that they are salts. That's what plants absorb as ions, cations and anions. And when we add a salt to water, it dissociates into its positive and negative charge components. Okay. Um, we talked about how we measured the total salinity of solution using an electrical conductivity meter. But we measured total, right? Not individual elements. It's important to understand that that doesn't tell you what's in the water, just how much of all the different charged particles. We discussed the different methods: pour through, saturated media extraction, and 2-to-1 dilution methods. And you should know how basically all three work, and you should know the advantages and disadvantages and uses for different ones. For example, doing a pour through on a large tree root ball is not practical. So you're going to be doing 2-to-1 or saturated media extraction on something like that. We also discussed pH and how it plays a role in nutrient availability. We'll touch on that again today. But this picture, there's many of these on the internet. Really, you should become familiar with them and to help you understand nutrient diagnoses and how pH impacts availability. And we're looking at a compromise, between giving up availability of major nutrients to keep minor nutrients happy, like iron. So today I want to introduce a term called cation exchange capacity. And the best analogy I have is a sponge. And this is a measurement of a soil property that measures its ability to store nutrients. Essentially, charges, so in the images here we've got positive and negative charges. The salts that are being watered into your soil interact with the soil, and they stick, like on this side, to the soil particles based on charge. And that allows the soil to hold on to nutrients. So you'll notice here that clearer water is coming out the bottom because the soil is holding on to the nutrients, where in this side, a lot of the nutrients are coming out the bottom, right? So it's the ability of the soil. We're measuring the ability of the soil to hold on to cations. That's why it's called cation exchange. And to help you remember what a cation is, I've got this goofy meme, right? They are positively attractive, right? That means that cations have a positive charge. Anions are negative charge. So it's really important to remember that. As far as plants are concerned, the major group of nutrients that we are concerned about are cations. Well, not all, but a good chunk of them, right? Anions like nitrate, phosphate, and sulfate are important, and we usually are supplying them in much larger quantities. But cations is what we're talking about primarily, positively charged ions. Yeah, so positively charged ions are attracted to negative charges on the surface of the soil. So soil essentially is made up of negative charges, which means it can only attract cations. It does not attract anions very effectively. So remember that. It's the positively charged ions that are stored in soil. I really like this picture, and you'll probably see it if you take more courses with me, because it really helps remind you of what's going on here. So on this side, we've got the root, all right? And we've got root hairs extending into the media, and the root hairs are putting out protons. And those protons will travel through water in the soil to the soil colloid, and because they are positively charged, they will dislodge cations, which then the root can absorb. So it's like they're cashing in their coins to get their magnesium and their potassium. So all plants can really do is pump out protons. That's really what they're capable of. Most of the time. There are some selective pumps that can pick up certain anions and cations, but for the most part, we're looking at proton exchange with soil surfaces. So they produce an acid. The acid goes into the media and dislodges the metals, the nutrients that then the root can absorb. So plants can only absorb what they need to grow at any particular time. There are some nutrients they're just greedy with and they'll keep taking them up, like nitrate. But generally speaking, you want to be able to dole out the nutrients as the plant needs them. If you put a ton of nutrients into your soil, knowing that the plant will need all that in its lifespan, but your soil is not able to hold it, it basically leaches out into the ground and it's lost. And you've just wasted your money and you've polluted the environment. So we have to understand what kind of soil we're working with, and that dictates what we can and can't do as far as delivering nutrients to help the plants reach their full potential. And that involves getting a measurement of cation exchange capacity. The soil particles that I keep talking about are called colloids. That's a term I'm going to use in the rest of the lesson. So colloids are the soil structural elements that have charged surfaces that attract the nutrients. Okay, those are called colloids. So when we were measuring electrical conductivity, we were measuring the ions that were free in solution. Right? Not ions that were bound to soil colloids. We were measuring ions that were in solution already. Whereas when we measure CEC, we're measuring the amount of storage capacity that soil has. In fact, in the lab, they often will knock all the elements off the soil with an acid wash, right? And then they can measure what charges are remaining on the surface, and that tells us what its full capacity is to store cations. That's the cation exchange capacity. So again, colloids are what stores the cations, and they are where the nutrients are, and the roots have to access them. So think of it as like a bank. You know, you put your fertilizer in the soil, it gets stored in the bank of colloids for later access by roots. And again, looking at clay, you can see how with its thin wafers and really high surface area, that clay can be an excellent nutrient resource. It's like all things in nature, it's a compromise, right? So we have fantastic nutrient storage capacity, but we have very poor aeration because there's not a lot of macropores. So obviously a clay loam or any soil that's a combination of clay is going to have excellent nutrition, for the most part, with some exceptions we'll talk about, but it's going to have other challenges like drainage and aeration. So everything in balance, right? Just briefly, hydroponics, obviously there's no soil involved, so that means there's no cation exchange, which means that nutrients are immediately available to the roots. The chemistry has to be in such a way. But it also means there's no reserve. So as soon as you forget to add nutrients, the plants immediately show nutrient deficiency because there's nothing in the soil to buffer and start releasing nutrients that you may not have right on time. So hydroponics, you can achieve excellent yields and productivity, but you need to be on the ball all the time to keep the crops happy. I mentioned these two charts already and how there's a difference between hydroponics and soil in terms of nutrient availability. If you look at this picture closely, you'll see that down here it says also soilless mediums. That's true to some extent, but not quite. So what you see here is like a true hydroponics chart. Soilless media has slightly less CEC than actual soil you would find outside, mineral-based soil, but it has some, so it's somewhere in the middle. But I think to play it safe, people like to say, well, we should treat it as if it's hydroponic. But it's somewhere between these two in terms of nutrient cation exchange capacity. Okay, so again, here's a really good picture outlining what the roots are doing. So the roots are pumping out protons or acid, which then dislodges positively charged nutrients like magnesium and potassium from the soil for them to be absorbed by the root. Another interesting thing which this picture is showing, and I haven't brought up yet, is that not only do the plants pump out acids, but just by the fact that they're alive and undergoing respiration means that they are producing carbon dioxide. And carbon dioxide mixes with water to form carbonic acid, which releases a proton. So what's really interesting about that is that as a plant becomes physiologically active, i.e. it's growing rapidly, it will naturally acidify the water because of its respiration at the roots, which will then also enhance the release of nutrients. So it's sort of they're self-perpetuating in that sense. So if the plant's growing more rapidly, it releases more nutrients from the soil. If the plant slows down growth, it releases fewer nutrients from the soil. Sometimes it has to actively pump protons out if it's really in trouble, like there's a deficiency. But more often than not, it's just simply their metabolic activity that releases the nutrients from the soil. So you might be asking, what happens to negatively charged nutrients? I mentioned nitrate and phosphate and sulfate. The reality is that sulfates and nitrates pass right through the soil. There's really nothing to hold them there. And they are, especially nitrates, one of the big causes for pollution, in the sense that when agriculturalists over apply nitrogen because they think, well, if I just add more, I get more yield. But if they over apply at a rate that's beyond what the plant can use, there's nothing in the soil to hold on to that. So some people like to use slow release fertilizers, but at the end of the day, if you are not matching the plant's needs, those nitrates and sulfates are just going to wash into the groundwater and pollute it. Phosphate is an interesting one in that it reacts with iron and aluminum in the soil, and it actually becomes immobile. Even though it's a negatively charged nutrient, it is actually very immobile in soil. So farmers often have to over apply phosphate to compensate for that, depending on their soil. So soils that typically have that sort of look like they have high cation exchange capacity, even though this isn't a cation, they tend to have high iron and aluminum content, which means they also immobilize phosphate. Something to keep in mind, phosphorus is an interesting nutrient. It's sort of one we typically don't see deficiencies of in greenhouse contexts, but in field contexts we do, especially in the spring and fall when the soil temperatures are cold. I'll talk more about that when we get into nutrient deficiencies, but that's why young plants go purple. Purple is a symptom of phosphorus deficiency, and often it's not because the phosphorus isn't in the soil, it's because it's not available. And as the soil temperature warms up, the phosphorus becomes more available. So some farmers will over apply phosphorus at the early stages to help the plant get the best start possible, but you have to be really careful that you don't have soil erosion because you will pollute waterways very quickly. Okay, so to summarize, cation exchange capacity is what CEC stands for. Cations have a positive charge. Cations exchange capacity is talking about storing cations. Anions have a negative charge, right? And they leach from soil. They're lost because they do not stick to the soil particles generally. Looking at different soil types, they obviously don't all have the same cation exchange capacity. I've got the example of a unicycle here, and I've got this chap who has a tremendous amount of boxes on here. I'm assuming they're quite light, but obviously he has a much higher capacity. Trying to create a memorable picture. So looking at soils, as far as increasing capacity, going from sandy to clay, we have increasing cation exchange capacity. So peat moss is okay, it's not stellar. Organic soils are definitely better, and clay has the highest cation exchange capacity. Looking at the solids, the colloids that make up soil, helps us understand why we arrive at different cation exchange capacities. And a lot of it's to do with weathering, so the age of the soil. I mentioned this earlier in the course, and we're going to talk a little more about it today with this idea that tropical soils are more weathered and have lower cation exchange capacity. If we're looking at organic or clay particles, they have these negative charges. You can't see, it's really small here. But what looks like this initially in the soil quickly turns into, the hydrogens are lost, quickly turns into lots of negative charges. So things like humus is huge. Adding compost, which is high in humus, helps increase these negative charged things in your soil. So adding compost to a garden may not add a lot of nutritional value, but it really improves properties like water holding capacity and cation exchange capacity. It doesn't mean there aren't nutrients there, but there are a lot of other benefits to adding compost. clay particles obviously have maximum amount of negative charge particles, so they have very high CEC for a colloid, whereas sand and silt, which are not as weathered and don't have a large surface area, are typically poor cation exchange. So sandy soils just don't hold on to their nutrients, right? If you go through Niagara, our soil in this region is quite interesting. There's pockets of land that are very sandy, and there's pockets that are very heavy clay. We're all over the map. There's pockets that are high in limestone. There's pockets that are not. It's really quite variable. You can have one farm beside another that has vastly different productivity and yields and challenges with root disease and pest pressure. A lot of it related to the soil that is on the land. So it's definitely worth knowing what you're buying if you buy some land for a garden or a farm, because the value will be dictated by the quality of that soil. You may think, well, I can change it, but realistically, to change quite a few acres takes a lot of time and energy and money, and not everyone has that. So they typically grow lower value crops that are less sensitive to poor quality soils. So sandy soils, which are excellent drainage, right? So in the spring they warm up quickly. They have good aeration, but they have poor cation exchange, and they have a lot of leaching problems. So farmers have to be very careful how they apply nutrients. So typically fruit farmers that are in sandy soils will be adding compost and manure as often as they can, not overdoing the manure because your salt levels can start to go up from all the salts in the cow urine. Looking at tropical soils, though, they tend to be quite weathered, and that seems to impact their cation exchange, right? So sandy soils are low CEC, tropical soils are low CEC, and clay and humus soils have excellent CEC. Looking more closely at tropical soils, they have what looks like good structure and drainage, but what happens is the clay has broken down so much that the layers actually flatten to the point where they are treated as a solid object. Which means you no longer have access to those layers for the cation exchange, and you don't have the charges available to hold on to the nutrients, and so they leach through quickly. That type of soil is called kaolinite clay. My best analogy would be like a stack of peanut butter and jam sandwiches. So clay that's not too old has got lots of good sticky layers between the clay structure that can exchange lots of nutrients and hold on to them. But as that clay wears and weathers, it ends up tightly packed, like over here, with no stickiness between the layers. And that means that they leach nutrients very rapidly. They don't store anything, and it's very difficult to achieve decent yields. It doesn't mean it can't be done, but there's things that have to be done to improve the soil if you're just looking at fresh land soil. Looking at clay in Ontario, where we have what was called temperate soil, our soils are not nearly as old. The clay looks like a sponge. These are close-ups here of what our clay looks like. So it's much more sponge-like and open. There's definitely a lot of surface area there, but it's not flat sheets like a ream of paper. There's air pockets and surface area in there to hold lots of nutrients. Can we fix soil like this? Can we fix the tropical soil? Absolutely, 100%. So adding compost and organic matter is a huge boost to soils that are heavily weathered. So, for example, farmers that have been existing for a long time in tropical climates that have been managing their soil will have decent yields. It's not like because someone's in a tropical country they don't have any yields. That's not true. But looking at the base soil, there are challenges. So we've talked a lot about compost, but we haven't talked about biochar, and I want to bring that up because where's my eraser? It doesn't want to click. It's a really fascinating story. So yeah, review again here, organic matter. So farmers will spread manure and compost on their fields. Here's someone putting compost in a garden in some sort of arid climate, and this is an enthusiastic composter. And as far as organic matter goes, in Ontario, a lot of farmers do what's called no-till farming. If you look at this, this is a relatively young corn crop, And in the ground, there is all sorts of dead corn matter from the previous year. And this matter will break down and form humus, which works its way into the soil, increasing its cation exchange capacity and water holding capacity and all sorts of beneficial properties. Same thing over here. Last year's crop rotting on the top of the soil. So no-till farming is very popular for preserving soil, prevents erosion, and increases your organic matter content, which improves your cation exchange capacity. In recent years, as in the last couple of years, farmers have sort of taken a bit of a break from no-till farming to try to break some disease cycles. So it looks like constantly doing this isn't necessarily the best either. But obviously, the majority of the time doing this is the idea would be good. But every once in a while, you need to till the whole field to break cycles, because bugs can nest in here, fungus can sporulate over the winter. As we get milder winters and there's less kill, these disease outbreaks become more common. So, in this picture, you can actually see how organic matter from the surface is slowly eluviating out or down into the soil, improving the soil's cation exchange capacity as you go further down. Down here, we've got sandy soil, which has poor CEC. And as the organic matter leaches down into the soil, it improves the CEC profile of that particular cross-section of the horizons. Okay, go back to biochar. So biochar essentially is activated charcoal. You've used it in your Brita filter. Any kind of water filtration that purifies it uses activated charcoal. And it's exactly the same property that does that. It's cation exchange capacity. So by having activated charcoal, it's got tons of negative charges on the surface. All those negative charges will attract positively charged molecules and atoms and take them out of the water, which helps purify it. Now, as far as biochar is concerned, it's taking typically straw or some other biomass that's easy to burn, and you burn it in a controlled environment. If you look carefully, this is a steel kettle. They put a lid on, and they limit how much air gets in there, so they can kind of smoke it for a while and then shut it down. And that means instead of getting a pile of ash when you open it, you get actually charcoal. That's how that's done. In the old days, people would pile a bunch of combustible material and then cover it with dirt. And then they would set it on fire and then cover it with dirt again. And it would smoke for a few days as it slowly burned. But because it was burning in low oxygen, you ended up with charcoal instead of ash. So obviously you didn't get all the heat and flame you would get if it was well oxygenated. You lose some carbon obviously from the combustion, but you're left with biochar. And the next picture. So there's lots of evidence that biochar was used thousands of years ago in South America, in Amazonia, and it was known as terra preta. That's probably when colonialists came in, because I don't think that's in the language that would have been used, but terra preta is what we have documented. And these pictures on the side are from a paper. There's a link down here to a paper that I pulled out. This is a couple of years old, but it's still a really good paper, that shows how recent fields that have been recently deforested have low yields. And by adding the biochar, they are able to improve the productivity. So here you see what a cornfield looks like on soil that has been recently cleared. And then after adding biochar, you can see all the black eluviation that's happening. The yields are substantially improved. And because the soil in the South American countries that are close to the equator are heavily weathered, this practice has gone on for a long time and has shown to improve productivity substantially. And what's really cool about this is that the biochar has a long-lasting impact on the quality and yields. Now, looking at biochar, it may be impressive, and it does increase cation exchange, but there is always something else, right? So, but wait. You don't want to just run out and go buy a bunch of biochar and add it to your Ontario soil, okay? If your soil is already productive, i.e. it has good cation exchange capacity already, and then you add biochar, having too much cation exchange capacity actually makes it very hard for your roots to get the nutrients away. and you actually decrease the nutrient availability. So biochar is reserved for soils that are low on cation exchange capacity. It's not something you automatically add to your soil. That's going to have some negative impacts. So it's best for poor weathered, heavily weathered soils. This is a chart I pulled from that paper that was looking at farms in Colombia. And this is over a 3-year span, 4-year span, 2003 to 2006. And you'll notice the gray line, the middle one, is where they add 8 tons per hectare of biochar, and the black one is 20 tons per hectare. And what's interesting is you'll notice the first year, the differences are minimal. And then, of course, as time goes on, the difference in yields improves. Now, you should understand farming is what it is. Every year is not the same total yield. This is grain yield. So, for example, 2006 would have been a bad year, hot and dry with poor yields. But relative to the control, so the white one is control, the first year there's no difference. Second year, there's already a difference. Third year, there's even a larger gap. And third year, there's even a bigger gap. In fact, more than double the control's overall yield. Where, here we're looking at maybe a 25% increase. Now we're looking at 125%, let's say. Why is that? Partly because when you add the biochar at the top of the field and then you try to till it in, it takes time for that to eluviate into the soil fully into the root zone so the plant can take advantage of the extra cation exchange capacity. The roots generally don't like growing on the upper surface alone. They're going to go down, and so if the soil below that hasn't really had the biochar eluviated down, you don't get that full cation exchange capacity boost. Then, of course, adding a fair amount is also helpful. But there's probably an upper limit, right? So 20 tons per hectare is quite a bit. I'm wondering if they'd gone to 30, if you would have seen actually a decrease in yield relative to the 20. Because now it's going to be hard for the roots to get the nutrients out. So too much of a good thing, right?